Hello everyone, and welcome back to Nanotech Byte Genius. In today's video, we'll explore the concept of a 4-bit full adder, walking through an addition example, and finally, we'll delve into verilog code to implement and simulate this circuit. So, let's get started. Let's start by understanding the basic building block, the 1-bit full adder. When you feed A, B, and C into the 1-bit full adder, it calculates two outputs. Sum represents the result of adding A, B, and C in, which is equivalent to the XOR operation. Cout represents the carryout from the current bit position, calculated using the AND and XOR operations. This carryout is then used as Cin for the next bit position. We'll be cascading 4 of these 1-bit full adders to create a 4-bit full adder. FA0 handles the least significant bit, LSB, position. FA1 handles the second least significant bit position. FA2 handles the third least significant bit position. FA3 handles the most significant bit, MSB, position. Each 1-bit full adder in the cascade takes care of its specific bit position. For example, FA0 calculates the sum and carryout for the least significant bit. The carryout from FA0 becomes the carry-in for FA1, and so on. This cascading mechanism ensures that each bit's addition takes into account the carry from the previous addition, just like we do manually when adding multi-digit numbers. Now, let's see how this 4-bit full adder works in action with an example. Consider the numbers A equals 1101 and B equals 1010. Starting from the least significant bit, the 1-bit full adder calculates the sum and carry for each bit position. 1 plus 0 is equal to 1 carry 0. 0 plus 1 is equal to 1 carry 0. 1 plus 0 is equal to 1 carry 0. 1 plus 1 is equal to 0 carry 1. As we move left, the carry propagates through the circuit. At the end, we get the result, sum equals 10111, where the MSB is the sum of the carries. Now, let's dive into the code that implements this 4-bit full adder in Verilog. This Verilog module 4-bit full adder implements a 4-bit full adder. It takes two 4-bit binary inputs, A and B, and a single-bit carry-in, Cin. The module calculates the 4-bit sum of the inputs along with the carryout, Cout. The always block contains the combinational logic that computes the sum and carryout based on the inputs. We need to test our circuit to ensure it works as intended. The primary purpose of a test bench is to validate the correctness of your design by generating different test scenarios and checking if the outputs match the expected results. A well-designed test bench helps catch errors, bugs, or unexpected behaviors in your design before it's implemented on hardware. We set up different test cases to cover various scenarios that our design might encounter during its operation. Each test case involves providing specific input values to our design and then verifying if the corresponding output values are correct. Delays are used between setting input values to allow time for signals to propagate through the design. This simulates the time it takes for data to reach different parts of the circuit. Alright, let's move on to the exciting part, simulating our circuit. Follow the instructions on the screen to open gtkwave. Follow the instructions on the screen to open the 4-bit full adder VCD file. As we can see from the waveform, the results show that the circuit behaves like a 4-bit full adder. We've explored the concept of a 4-bit full adder, seen an example in action, understood the Verilog code, and even simulated the circuit to visualize its behavior. If you found this video helpful, don't forget to hit that like button, subscribe for more content, and as always, feel free to ask any questions in the comments below. Thank you for watching.